Hello and welcome to the Cuyamaga Institute, our Q&A Conversation for Exploration series. I'm Paul Robert, the Executive Director and President of the Institute, along with my wife, Laura Lee, the Director of Research, Education, Outreach, and on behalf of our Board of Directors, advisors, volunteers, supporting members, we do want to thank you for joining us today. The Cuyamaga Institute is an independent, nonprofit research organization committed to researching consciousness and following the story, the human experience, the footsteps of our founder, anthropologist, Dr. Felicitas Goodman. Each of these Sundays, we have this ongoing exploration. So as an educational institution, we take an open approach and we invite scholars in related fields that help broaden the scope of our own work and exploration. And that's why we call this Conversation for Exploration. And really, at the foundation of this institute is the role of being the observer. Observation on the level of the inner vision and observation of the world around us is at the very origins of this institute. And it was the observations of Dr. Goodman, our founder, as she was looking at the worldwide prehistory artifacts and wondering, how can we interpret these elements left by these ancestors? And she did conclude that these images may include ritual instructions. That's a much longer story, which we'll share with you another time. But today, when we look at science, and we look more specifically at astronomy, we continue to see the extension of our own inner exploration being expressed in the outer, the observing the amazing combination of elements that brought about life, in which science continues to peel apart to discover. It's a verification of this incredible journey of humanity, and we continue to enjoy. And with the recent images coming from the Webb telescope, it's revolutionizing astronomy. It's pushing the outdated theories and opening up new perspectives on life itself. And what does this reveal about ourselves? I mean, we're at this critical stage of humanity. We're ready to fully embrace the miracle of life, see our relationship with the universe that encompasses us, or we will continue to have blinders on and not have the full view of what it is to be living this life in such an amazing and miracle way. American astronomer Carl Sagan, he put it this way, quote, "The way to find out about our place in the universe is by examining the universe and by examining ourselves." And he also notes, we are a way for the cosmos to know itself.
And I was thinking about our common drive, and what is it but to explore those unknown vistas? What is our worldview's evolution but a series of paradigm shifts? And what has been there throughout time, beckoning us on so many of these journeys but the stars? And today we'll discover how astronomy and the study of all celestial phenomena has lit the way for the most monumental of these periodic disruptions, with the promise of many, many more, as we've invented technology to see further and further out beyond our own eyes' limited view of the electromagnetic spectrum. The cosmos, as a vast sea of energy, has made herself more and more visible of late. To our telescopes and our latest crop of instrumentation, and with the promise of the next generation, she is sharing her secrets, letting us get closer and closer to the magic of it all. And to recount that journey, our guide today is Tony Hull, astronomer. He helped develop NASA's next generation of Spaceborne Flagship Missions, the Habitable Worlds Observatory, and along the way participated in spaceborne missions at NASA and in industry, led the 60-person team over 5 years, polishing the suite of the James Webb Space Telescope mirrors, and is now professor of physics and astronomy at the University of New Mexico. But perhaps his favorite role, certainly the most fun, is as friend and member of the advisory team to the Cuyamaga Institute. Hey, Tony.
That's obviously tongue-in-cheek. It's our gift to have Tony in our community, and we're so happy to have you here, Tony. And I know we started off.
And welcome back.
Yes, welcome. And so let's start from the beginning. And I know you sent me a few slides, and I'll open those up in just a moment. But let's just give some context to where we're going with this conversation today.
Well, Tony, I have to know first, how did you what call to adventure did you answer? What was your first inkling that the stars would be your milieu, your neighborhood, your quest in life to understand?
Well, I can go way back to as young as I can remember, and I had what I called the blue dream, and I was flying through the stars. And then, starting when I was about 8, I grew up in a farmhouse in northern Connecticut, a very old town in northern Connecticut. And I would crawl out on the roof of the porch and then go up one level higher, and I'd lie there and I would just look at the skies.
Right at the
And this
right
was
angle,
about
that roof too. Yeah.
it was perfect angle, yes. It was aimed away from the adjacent township lights and stuff like that, so it was really nice. And then I had a mentor down the street who was, Clinton Ford, who was a very avid, very prominent amateur astronomer. He was the right at the core of one of the major associations of amateur astronomy, though not a very professional level, the AAVSO. And he started mentoring me. So I started uh, being totally absorbed in magazines like Sky and Telescope and things like that. My
And you
mother
were
looked and
hooked.
thought, "Oh, what a terrible nerd! How could this ever come from my genes?" So, at any rate, it was uh, this has continued, and it's not been a linear path. It's been very nonlinear. Though
Like
I've
most
always
of
loved
us.
astronomy, and this has been the core of it. But instead of going to study astronomy in college, my family said no. It's too arcane. They thought astronomers just looked through a telescope, and and nobody would ever want to employ an astronomer, and how terrible that would be. So I went to engineering school at the University of Pennsylvania,
Mm.
uh, which was fine. I took undergraduate and graduate astronomy classes as my non-technical electives.
Oh,
I
very
had
good.
I had summer jobs for 3 summers in astronomy, including a sophomore college, which was fascinating, and
Mm.
then at MIT. And it just it just sort of worked out. I wanted to take a class as a freshman. Engineering curricula is very, very full, but there was only one section of beginning astronomy I could sign up to. So I was sent to the chair of the department to see if I could get in. That section was already full. And I said, well, I love astronomy. I've been doing this in variable star observations. And he spoke like this. Well, I think we have another class you might like. Well, he threw me in a class where I was competing with 2 graduate students, two junior majors and 2 senior majors.
Oh,
He needed 7 for the
juicy.
class to run. It was
Yeah.
very juicy. I learned a lot, and actually, this enabled me to get the summer jobs I had.
Wow.
And even when I went to MIT, this class had studied one of the things I'm going to talk about in a few minutes is time, and astronomy and time are integrally linked.
Yeah.
And the way time was determined throughout the 19th century and before was by a device called a meridian transit.
Mm.
And this would be used to correct and set clocks. And
Oh,
so every city had their meridian transit. And so I learned how to use a meridian transit. Nobody at Harvard or MIT had ever thought of looking through a meridian transit, but I had taken it as an exercise in observation and in reduction of observations as a freshman.
okay.
So I got to this brand new antenna that MIT had constructed, MIT Harvard had constructed. It was called and still is called Haystack. It was 120 feet in diameter, and it was the most accurate antenna of this wavelength ever made.
At its
But
time. Yeah.
at its time, and still is right up there.
Oh, really?
and 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 it's in a huge radome, so it looks like a great big golf ball. It was wonderful, except for one thing: they couldn't figure out how to make it point correctly at
Mm.
radio stars. And
Okay.
so I was assigned to work with a technician, and I'm sorry, it's a little bit of a personal story, but it's kind of
Yes.
how things have worked out in life. It's part of the magic too.
Mhm.
So was assigned to work with a technician who would drive the antenna, and I would observe, and I would look at how much I had to offset the antenna to really find Cassiopeia A and the galactic center and this and that source. And I was making up vector diagrams that my boss had dreamed up. And I was doing this for nearly 2 months. And then I woke up one morning in a dream. I knew the answer. It was nothing but this class I had taken for upper level students, but I took as a freshman at the University of Pennsylvania in 19th century astronomy, the meridian transit. And I used the equations used to correct the meridian transit that had been worked out beautifully. That
Wow.
was a time in the world where people understood spherical trigonometry. And, and so I learned spherical trigonometry, and I learned error theory. And I walked in and I told my boss, his name was Lit Meeks, here's the answer. It
Yeah.
is nothing but a meridian transit problem, but we have 2 more degrees of freedom. And immediately I was assigned a computer programmer, and we solved the problem. And the method is still being used for every large radio telescope and altitude azimuth telescope in the world.
My goodness.
But
Wow.
this is an accident. How did I get in this class, etc. So
Destiny.
anyway,
Yeah.
so this is part of the mystery that things kind of click together, and I don't attribute it to any great talent I have, except
Yeah.
that I kind of expose myself to situations where different things will happen. So it's a little bit of the mystic side of astronomy.
Mhm.
Could we go to my slides?
Sure can.
Well, he pulls it up. I was just going to say that we just try to operate by what we call the cosmic clock and just
Yeah.
let nature and the universe put us where we're supposed to be at the right time and everybody else in our orbit. So I think it's such a handy metaphor for that, the wheels turning of the universe that has a grander plan in mind for all of us.
Okay. Well, these, if you can go into projection mode, Paul, and I love the title that we kind of came up with yesterday when we talked, the progression of disruption. And one of the wonderful things about astronomy and about science is that there's constant change, and that's going to be one of the themes of this. And there's a picture above of the Webb telescope. An unbelievably complex machine. It's been described as the most complex science machine ever developed. There's people in accelerators might debate that, but it's right up there. And on the right-hand corner, you can see one of my technicians polishing one of the mirror segments here. There were 270 square feet of beryllium aspheric mirrors being polished. Uh, it may sound trivial, but let me mention there were 334,000 operations to do this, involving moving the mirrors, measuring, getting it back and forth, and team of 60, over 5 years, and we got it right. And so that was something that was a big part of my life. It involved a lot of pressure. It was under the microscope from Washington and all over the country. If anything went wrong, we'd have herds of people coming in to investigate. And they
Oh,
would
wow.
always ask me, this was being done above Berkeley in Northern California. And I used to love it that they'd send these elite teams in. And somebody would always ask me, are you aware there are earthquakes in Northern California?
Uh,
So I went, no, I did not know that. uh, well, anyway, we did everything we could, and there's a point where you cannot protect against earthquakes, but we did all the logical things on that. And what this is about is the look beyond. Maybe at some point, if you are intrigued, we will be able to go and show some of the amazing, moving, emotional, visceral images that come from Webb. And we're beginning to understand not only what these amazing images, that these are amazing images, but
yeah.
we're beginning to look at how this is disrupting our views of the universe in almost every way, everything from planetary science to the very early formation of galaxies. Okay, so this is kind of a very personal point of view. Um, there's an intuitive world that we as individuals have. It's based on our experience, our observations, maybe our inner sources. It could be based on many, many things. And then we go and we couple that with the scientific method. And there is an overlap to this. The scientific method is a filter. And we start with imperfect observations, just like I made imperfect observations for 2 months. And then all of a sudden something else clicked. And then the observations and the methods all changed uh, once that realization happened. But that came from the intuition. And although we were doing something scientific before, it was not converging. Well, then we went into something that converged, and that's a very nice thing that happened. And then we also have something that's problematic, and that is uh, that dogmatism can often attempt to suppress that comes from the intuitive or from the scientific method. And dogmatism I see as being somebody else's perspective as opposed to our own. So it can intrude, and it can impose beliefs and can control motivations. And there are plenty of examples of that in the history of humankind. The next slide. Well, here's kind of a view of how I think astronomy fits in. Uh, so let's start with I kind of go around the clock here, and let's start in the top. Astronomy gives us a sense of direction. We all know about the North Pole. The North Pole was not always where Polaris is. It's moved quite a bit and through the time due to precession of the equinoxes. But we've had a sense of what's east and what's west, and what's north and what's south. And this has been fundamental to virtually every society, and it superimposes upon the landscape, the uh, the oceans, the mountains, etc., that are around us. But this has been huge for us, and it has been the source of navigation everywhere from Polynesian migrations to the sailors of old, and even airplanes for till not all of that long time ago, and within our lifetime, if they were going long distances, particularly over the ocean, would have the ability to navigate with the sextant. And some people still know how to do that, though GPS is making that kind of less necessary. Uh, Astronomy can give us a worldview, and it includes astrology. And of course, I'm not going to go into that, but that's a fascinating topic. I know there are many different kinds of astrology. As our friend Fred Smith can talk at depth about that of India, which may be different than other schools. But it's interesting to see what that is, what that means. And to continue, there is a celestial mysticism that happens around the sky. And this may lead to ceremony. And maybe on the less attractive part is dogma. Astronomy now is things, temperatures and pressures and nuclear reactions and mass flows and things like that that are unimaginable on Earth can be observed, and we can see what happens at the extreme end of things. Going up to the top again, we see time, so we're going to go counterclockwise. And I mentioned the 19th century use of the meridian transit to define time. And not only time, the time of day, the sundial, the other techniques we can use to define time. Astronomy also defines the seasons. And in this format, I've talked a bit about my use of seasonal markers here. My seasonal marker for the equinox just passed, and the sun is racing south towards where it will be at the December solstice. Um, Astronomical events have defined hunting and planting, uh, and and this has been something true of many cultures. Going back to sacred art and architecture, one of the things that interests me, and we've talked about a little bit in the past, is how many buildings on the Earth are aligned not to terrestrial features, but to celestial features. We have the Great Pyramids, we have the Taj Mahal, we have buildings throughout Mesoamerica, we have Chaco Canyon, we even have some of the churches that are aligned in this manner. And it's a little tricky to do that, but I think we have a method that we've talked about, and actually Paul and Laura have implemented. I guess both at Kayamunge and at Sedona, where the broadcast comes from. It's called a gnomon, and it's a way to find out the cardinal directions. In other words, the cardinal directions are that of the celestial sphere, the cosmos, the realm of astronomy. So I see these things entering in many ways. And as I mentioned to you earlier, astronomy has come at me, maybe in some ways through virtually each of these ways. And I see that Michael's on. He has experience in astronomy, and he might want to comment at some point. But yes, these are all elements of kind of what goes on. I'm very pleased and gratified to live in a place where I have good horizons, and I can see the sunrise and sunset every day of the year. This means something to me, though I have to say how alarming it is, how fast time is moving now. But that's a kind of a interesting question, maybe for all of us. Uh, I just acquired a book, and I wonder if any of you would want to comment on it. And that is, why do clocks run clockwise? Does anybody want to comment on that? Laura looks like she has an answer.
As opposed to counterclockwise. But no, I want to hear your answer.
Okay. Well, I think it reflects the same way in the northern hemisphere. The shadow of a sundial goes around.
Ah,
And so clockwise, it may be northern hemisphere centric, and I don't think clocks in southern hemisphere run backwards. Though I think there are a couple of examples in Europe of clocks that run backwards. I know there's a big clock that is only one hand because no one obviously needs to know the time better than what you could indicate with the hour hand. Okay, yeah, this is an introduction. This is a book that came out in 1958. I acquired it in 1958. It's by the astronomer Harlow Shapley, who is one of the people who unfolded our understanding of the universe in the first half of the 20th century, of this. And it's called The Stars and Men. And he talked about a progression going forward from um, one level of understanding to another to another. And I would say all with delight, not with resistance. Here. So if we could go forward to the next slide. This is one that maybe much more detail could be added, but it's the understanding of our universe via astronomy. And initially, our universe, when we came out of caves, when we were, etc., were our immediate neighborhood, surrounded the valley I lived in, whatever. And then it might be advanced. Many of us were hunter-gatherers to our hunting grounds. What was the extent of that? And then we began to see my continent, the ocean bound, maybe the flat earth, we didn't know. And one thing I need to say and emphasize is that the understanding of the round earth and the sun going around the earth uh, was discovered at very different times in different societies. Things were discovered in Islamic culture, in Greek culture, in Egyptian culture, in Chinese culture, in Indian culture, and maybe even oceanic culture, and on a comparable time scale to that, or maybe well ahead of that known in Northern Europe or Europe. So this is always interested to me. I remember teaching years ago the way the Egyptians could measure the radius of the Earth by by measuring the distance, measuring the sun going down deep wells that were vertical, somewhat
Ah,
distant apart. So from that, if they did that, then they waited a few minutes later and they could, or an hour later, and the next well, they could measure that. And from the time difference and the distance difference, they could infer the diameter of the Earth. And so these things were known even before the time of Christ, but you wouldn't know that, particularly from reading the European literature of
Well,
this.
I heard also, Tony, that it was sailors or watching from shore over a vast ocean. You could see the tips of a sail long before you could see the full boat. And so that also implied the curvature of the Earth. Is that true as well?
Oh, that's absolutely true. Although somewhat alarming, there are still people who deny that the Earth is curved.
Well, they weren't watching that ship come up, were they?
Yeah, yeah. No, you definitely can see that, and that's a very good observation.
You get high enough,
Observation.
you can see the curvature.
Yeah,
Just,
and yes,
yeah,
you have to get up high
mountaintops.
to see it. You have to
Yeah.
get up high to see a distance, and
Mhm.
that's certainly very true. So we began to have an Earth-centric concept, and this led to all sorts of interesting things. Then we had, of course, Galileo Galilei in Italy, who not only did the gravity experiment, but he observed through a small telescope Jupiter. And what did he see? And if any of you have binoculars and have looked at Jupiter, if you look at it with a small telescope or binoculars, you can see it. But then you look at it again a few hours later, and the four bright moons have moved. And Galileo saw clearly that they were going around Jupiter, but it was against the canonical understanding of the church that anything that the Earth was the center of the universe. And so there is actually a book out on the sin of Galileo for observing that the moons moved around Jupiter, that here was evidence that something happened other than the order. And it was amazing, amazing the complexity that people went to try and explain the motion of the planets and stuff like that. We had circles rolling on top of circles around us, doing all sorts of things to explain prograde and retrograde motion of the planets and things of that nature. But that was what we did, and then we began to see that maybe the Earth was not the center of the universe, and we had the sun-centric universe, and the Milky Way-centric universe, and this we're going to a point that's not all that long ago, the early part of the 20th century. It was not at all clear that we had a universe the way we know it now. It was quite different. As a matter of fact, when I was growing up, the Andromeda Galaxy was referred to as the Great Nebula in Andromeda. We knew it wasn't a nebula. This is the most conspicuous galaxy in the sky. It's over 6 moon diameters in extent, and in a dark sky you can see that. But it was thought to be a big gaseous nebula like the Orion Nebula until well, just a little over 100 years ago, which so we began to see that Andromeda and other galaxies were not other objects were not nebulae, but they were actually galaxies.
And we could see
And this,
that when we got sharper
yeah,
and sharper vision. And
yeah,
Tony, at this point, could you just please talk about how disruptive it was for church doctrine to embrace when it finally had to, that everything did not revolve around the earth. I mean, really, our world and our place in it is so much an anchor of our worldview that when this self-evident observation became accepted, it really was a huge disruption. Could you just speak to that for a moment?
yeah,
How
yes,
much
of
we're
course,
dependent upon just
of
our
course.
understanding, our
Sure.
basic understanding.
Well, yeah, I mean, faith had been based around this. These were pronouncements, and and those who were supposed to speak impeccably of the world had misrepresented. And so this was again each one of these is a bit of a disruption in one way or another. This was a big one, and this
Yeah.
this rippled in various ways here. I will say that there was a response. The Vatican implemented the Vatican Observatory, and they had uh, astronomers working actively at the Vatican Observatory and contributing to astronomy at that point. They began to see that no, it's a little dangerous for me to go outside and say, here's the truth, when in fact instruments could begin and critical thinking could begin to discern between truths and non-truths. So anyway, we are, each one of these has been somewhat disruptive and not always met with a lot of happiness. So then we began to recognize that we had a local group of galaxies, and then then went on to see, of course, we began to develop what's called the distance scale, and and this is based on Cepheid variables. There's a certain class of Cepheid variable stars which change in brightness, up and down in brightness over a time scale of let's say weeks.
Hmm.
But there was found to be a correlation between the luminosity, the intrinsic brightness of the star, and the period. So even though the star was very far away, much farther than we could measure,
Oh,
well, we could measure some of them that were near us, and use traditional parallax methods and calibrate them. And then we
uh,
were being able to use this as a way to establish a distance scale. So we know if we observe a star, we know what its luminosity is. If we know what its luminosity is, the distance is proportional to the inverse square of that luminosity. So we began to develop a distance scale, which was quite wonderful. And I left off that we began to see that there were clusters of galaxies and superclusters of galaxies and all sorts of things happening. But we then started shifting to models of the universe. And when I was a boy, there were three models. One was the Big Bang model, which is now very much accepted and preferred. There was another one done by Cardinal Lemaitre of the Vatican Observatory, which was called the oscillating universe, or somewhat irreverently, the Bang Bang one, where it would expand, then condense, and expand and condense over and over again. But it would have the same artifact of expansivity. And the third was the steady state, and that was that the universe just keeps on going, doing whatever it's doing, and will never change. And that's, of course, been uh,
overturned.
gone away for that. Well, what we discovered with the expanding universe, this means that if we're expanding, it means that objects that are away from us are seen to be have a radial velocity. That means they move away from us because of the expansion. And the farther out you are, the bigger the beach ball that holds these, uh, the faster the radial velocity is. So
Hmm.
we have another method to indicate distance,
Mhm.
and this has been really critical of this. So we have more and more, and this is an artifact of the Big Bang, and uh, and this is how much of the distance scale of the universe has been bootstrapped out there. Well, back in about 1962 or 63, I think it was 63. I didn't have time to go and research this, but Bell Telephone Laboratories in New Jersey was calibrating the the microwave communication horns. I don't know if any of you have seen these. I should have included a picture. They're kind of like a big horn lying on its side, and these were used for efficient data transfer over a long distance. They could be pointed directionally,
Hmm.
and they were calibrating the horns. And whatever they did, they always had noise after they tried to understand and take out every noise source. There was this darn noise, and they couldn't get rid of it. Wherever they looked, they found that, and it was pretty much the same. Well, it turned out that that earlier theoretical predictions of the Big Bang had said that there is a residual temperature in space. And this is what radio telescopes measure. It's called temperature. And that temperature should be about 3 degrees Kelvin, very close to absolute zero. If the universe was aged as it was, then we thought it was 4 degrees Kelvin. Now we think it's 2.7 degrees Kelvin, but it's still the same thing. So this was totally accidental, and it was by Penzias and Wilson. They recognized that this observation, calibrating communication equipment in a very, very precise, thoughtful, well-controlled way, this residual had to be that of the universe. And of course, that was verified in many, many ways in Antarctica and experiments all over of this. Well, then we go on, and I'll mention Kobe specifically. And this was a spaceborne mission designed to look at the residual of the Big Bang in all directions. And John Mather, John was a leading scientist on this, and he was able to determine with Kobe, which I think it's cosmic origin something something, I don't remember. He was able to determine that that the Big Bang is not the same in all directions, that there's a directionality to it. So all of a sudden we had cosmology that had been purely a theoretical science turned into an observational science. And as I said, John won the Nobel Prize in 2006 for this, and John went on to be the principal scientist for the Webb telescope. And during this period, we had Hubble, and we were seeing the universe in all sorts of ways that we hadn't. Everything again from the solar system to deep space, and Hubble looking out in the darkest area in the sky near the Big Dipper, thinking they were looking at total empty sky. Nothing had been seen before, and they stared at it for a number of days, nearly 2 weeks. And all of a sudden, they saw that this place where there's nothing was just filled with thousands of galaxies. And this was called the deep field, to be followed by the ultra deep field, which was very illuminating and very much in the causality and the intent of the Webb telescope. And I'll also mention LIGO, which is the gravity wave experiments. And astronomy was shook about 6 years ago when a huge gravity wave event happened from the merger of two neutron stars very far away from us. And I think over 5,000 astronomers all around the world turned every instrument they had onto this to try and understand what happened in this huge, extremely violent, dramatic event that changes the gravitational field where we stand. And all this is part of what's led into Webb, and the pictures, which we will show on another occasion of Webb, will give you an indication of what we can see with Webb that operates at a different wavelength, that's much larger than Hubble, that has different instruments than Hubble, what it can see and what it can tell us, the secrets of the universe that were hidden by Hubble with Hubble observations, because Hubble could not look in the infrared the same way Webb can, are now emerged. We see all sorts of detail, giving us all sorts of understanding we didn't have before. And Webb was also optimized to be the first telescope to see the first light from the first galaxies in the emerging universe, which is, it's kind of a mouthful. And in fact, it is telling us something. And what it is telling us is that galaxies formed much earlier in the universe than any of our theories. And again, another disruption, and astronomers are very excited about this. And over the course of the next few months, we're going to start seeing more and more scientific papers on this. But again, every time we look, every time we develop a new instrument, a new way of looking, we both see things that we hope to learn about, and then we find whole areas where we'd not even dreamed that were happening, where things are totally different, and this makes it exciting. So we have several telescopes on the landscape. I can't go into them all right now. I'm involved with the next large space telescope, the Habitable Worlds Observatory, and this is designed to do direct imaging of habitable Earths around other stars. So we'll have a whole different idea of what our world is like. It has to give you an idea. We're talking about maintaining stability of this to make this observation, and it will be roughly the same size as Webb, but having to be stable to a few billionths of a millimeter, billionths of a millimeter, very, very small numbers. We're getting down to the size of the atomic sizes. So this is the sort of thing that we're going into in the world to come.
So just a couple of questions, because that chart was fascinating for the whole evolution and where all that instrumentation and inventiveness has taken us. But first of all, our inability to see the details led to our mistaken assumptions of emptiness. So that's true with the deep field. We thought there was nothing there because we couldn't see it, but that was really just the limits of our own observational powers. And so then you create more instruments that see further and further with all this different spectrum of the electromagnetics. And then we see suddenly things come into view. I mean, how incredibly fascinating, Tony. And I suppose the same is true with dark energy and dark matter. We call it dark simply because we don't know what's there, right? It looks dark to our eyes, but our eyes aren't the only aren't the best instruments for viewing it.
We know it's there, but we know that it cannot be observed by traditional methods. But there are indications that it's there. We see it reflected in the dynamics of galaxies and things like that.
We know a lot's there. We just don't know what it is. Yeah.
We know this is dominant in the universe. And
Yeah.
it's not because, I mean, that we're aware of it is a tribute to science, not a complaint of this. And we have to keep on looking at new and better ways to find and see things. And who knows? I mean, maybe we'll learn. We're going to be launching the LISA program. This will be about a decade off, which will be a series of satellites that will be even more sensitive to gravitational waves. Maybe we'll see some of it that way.
Okay.
We're looking at doing new X-ray telescopes. Maybe this will be manifested in energetic events that happen for no other reason because we do not see the hydrogen gas or the molecules or the dust that we would expect to see from the visible and infrared.
Can you give us a hint of some of the projects and some of the meetings that you're in on about how they're thinking? What is the quest for some of this next generation of space telescopes and instruments?
Including AI, with the intense activities of AI and how it's now become the mainstream is being aware of it, even though AI has been around forever. But that's going to definitely be impacting NASA and the discoveries and what's happening and the whole thing.
The robots will be sending out. What's on the horizon that you can give us a glimpse of?
Okay, well, near term, we have the Vera Rubin telescope, which is going to be magnificent. It is designed to look at the entire sky in the hemisphere twice a week.
Mm-hmm.
It is the computer with the telescope fastened to it rather than the other way around. And I'm sure that AI is prevalent on that. One of the things that we're finding with some of the rich survey telescopes, that the data is so abundant that even all the astronomers in the world cannot by themselves do things like classify each of the galaxies that is seen. And actually, it's even been ported some of this to citizen science, where citizens have gone and done this. And when they kind of test and evaluate that done by astronomers versus that done by trained citizens, the results are the same. They're, that the people who care and are looking carefully and have criteria are doing very similar work on that. AI can take this a step further. It's one of the major things that it can do with us. It can help us reduce data much, much more rapidly. And particularly in the event of, let's say, an event with either the LIGO interferometers that are used for gravity wave here on Earth or the LISA, um, a gravity event, when detected, there will be dramatic changes over the time scale of minutes and hours. And so the ability
Wow.
to divert world's major assets to look at the object where this is happening immediately, as
Mm.
opposed to somebody sitting on it for a few days and then there's no way to observe this and that, and you can only.
Mhm.
But here's the ability to go and look at something in real time as it's happening. Real time, it may have been happening 1,000 years ago, but it's when it's seen here, of course, because of space time.
What are some of the secrets? What are some of the theories? You mentioned the formation of the galaxies happening much earlier. What are some of the other major hallmarks that are being overturned or rewritten or rethought in astronomy? And how does
Well,
that impact us?
there are many things. One of the things that's been remarkable is the activities over the last 25 years looking at exoplanets.
Yeah.
And we've gone from a small number to well over 6,000 that have been observed now.
Yeah.
One of the one I was going to talk about, it's a planet about the size of the Earth. However, it orbits the sun in something like 15 hours.
Okay.
So
Yeah.
it's kind of a sea of lava, the whole planet. It's all molten rock
Ice. Yeah.
and carbon and maybe even molten diamonds. It's a very, very different kind of thing. What we're finding is that there are many solar systems that have no similarity to our own. In our own solar system, we have the four smaller planets, Mercury, Venus, Earth, and Mars, and then we have the giant planets, which are Jupiter, Saturn, Uranus, and Neptune, and then we have Pluto, which is kind of an outlier. It's now called a Kuiper Belt object,
Mhm.
and there are others that are in the outer solar system, a belt of bodies that maybe don't quite qualify as planets, but they're out there orbiting. So we had thought maybe in our arrogance that other solar systems would be like this. But instead, we're finding other solar systems where Jupiters are as close to the sun as Mercury and things like that.
Wow.
So it's a real hodgepodge
Mhm.
of what's emerging, and it's kind of like how fascinating is this?
Yeah.
It's fascinating because we're so lucky that all the parameters came together to support our little biosphere and our atmosphere. I mean, I think we're kind of a rare jewel out there, it
Of
sounds
course
like.
we are. Yeah. I
Yeah.
mean, that was the point of this conversation for me, Tony. When I called you yesterday, I said, Tony, you know, I just want to understand and the perspective of how, as humanity continues to explore the outer reaches of the universe, when is it that we're going to realize what an amazing uh, set of circumstances that brings about life and where we're at and can
We have a
how we
well-equipped
can
little
own that
spaceship.
rather than continuing with that
Yeah.
the blinders on of humanity who sees everybody as separate, and we have different countries, we have different people, different nationalities, ethnicities. One person's this, one person's that, and we all think so separately. And when are we going to understand? It sounds like some kind of new age kumbaya, but the reality is we are all one. We have no choice. We're one.
Well,
Uh,
one of the things I love about astronomical observation is that everybody can look at the data.
Yeah.
Everybody. And that's one of the provisos that's becoming very standard with NASA, that is open data. Even if I was to win
mhm.
a proposal to implement a mission with NASA, the data would be open. As soon as the data can be calibrated, which might be hours, particularly with AI, as Paul was mentioning, it's released and you can interpret it. Somebody in India can interpret it. We can all go and look at it and discuss on this common point, this common reality touch
It's
point.
all our
It's not
legacy.
it's not going to be my telescope says this and your telescope says that. It's going to be
Mhm.
here's data that we can all look at, and communicate with. So that's something I find kind of rich, kind of appealing on this. And I also see this, that we're looking into the mystery. We're seeing more and more things that are applicable. And I'll even go a little bit farther at that. Uh, my theory of discovery, the story I told you about the pointing of the haystack antenna, I think this is much more common than you think in science. I know there's the story about Edison doing 10,000 experiments before he got the light bulb to work. And that may be, and there are certainly examples of that. But very few people have time for doing 10,000 experiments unless you're doing nuclear fusion right now. Uh, uh, and there is a source. There is something that starts. You look at a problem, you look at data, you look at images, and all of a sudden you get an inspiration. Where does the inspiration come from? This is an interesting topic,
Yes.
which we could expand
Much
on. And
discussed here. Yes.
yeah, 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 very, very appropriate. But the inspiration happens, and then you go and you look at it, and you put it in the scientific method. And this means that you apply it to certain tests. And sometimes you cannot repeat things. For example, I've observed several novae as they've exploded. These are stars exploding, and I can make observations from that, but I can't make it explode over and over again and to show people. There's certain limitations to what we can do, things
The
that
one-off.
are transient and one-offs, but we can, in the larger context of things, look at them. How does this nova compare to that nova, to that nova, to that nova? How does this compare to other observations, other wavelengths that are made? So there's a lot that we can learn, which but again, it goes back, I think, to my theory at least, and that is, if we care enough to observe uh, and pay attention as opposed to not, and then something is going to happen which may be revealed to us, and then we go out and we test that. And if it's how you grow your garden, that's one thing. And if you're going to go out and tell the world this is the way it is, it's another thing. The stakes are higher there. But I like that because it elevates this. Science is a method. Science helps us sort through things.
Sort through the
I
noise. Yeah.
sort through the noise, and I've given lots of presentations. I was NASA's technologist for terrestrial planet finder before Webb. And I used to go out and give a lot of public discussions, and I would come up across people that would say, "Well, my belief is that this and this and this happened, so I don't." And I keep on saying, "Well, what color do you think the sky is?" And, "Well, I think it's orange. You think it's blue?" "Well, I believe it's orange." What are you going to say about it? It's
Your eyes are tuned
uh,
differently, I guess. I don't know.
yeah,
Yeah.
that we need to calibrate your eyes type of thing, or
Yeah.
my eyes
Mm.
here. But the answer is, I think part of the answer is where we can make observations that are objective. We should do that. And is science perfect? I think the method is really good, but is there a politic in science? I would say yes and no. It's been fairly rampant in anthropology and archaeology. It has been far less so in astronomy, with the exception of things like religious dogma and stuff like that. Uh, Astronomy seems to have been, since the Dark Ages, fairly open to the excitement and exhilaration of discovery.
So, how is it possible that private companies can go to space as opposed to just government missions? I know that when cell phones first came out, you had to get a license to operate in our ionosphere, that this is a shared layer of the planet. And, you're going through space, you're putting in objects in space. How is that governed? I mean, where's the licensing involved that private companies can go through space? Just a brief question. And then what do you think the success is going to be or not of colonizing the nearest bodies, the moon and Mars? I just was mentioning that to Todd Van Poel, anthropologist, and he made an astute observation. And he said, all the pioneers through history had to struggle just to survive. So when you have some rich technocrats think that they're going to go colonize another planet, I don't know if they really realize the struggle they're setting themselves up for just to hard scrabble new land. Even if it's on another planet, just think about the added complexities that you're facing. So I wanted to really get your take on all of that.
Let me answer it in inverse order. I think they're fascinating questions both. Colonization of other planets, and there are really three candidates that I think are practical to think about. One being Venus, one being the moon, and one being Mars.
Just because of distance, right? The closest ones.
Well, because of the distance and other factors. All three are in what's called the habitable zone. It means it's not too hot for liquid water to exist, not too cold. So there's the possibility of living in any of these three, except Venus could be colder, but it has what's called the greenhouse effect there. It has very heavy clouds. The clouds are fairly concentrated sulfuric acid.
It's so good for the lungs, that sulfuric acid. Yeah.
Oh, it is. It really clears the nasal passage out.
Oh,
yes.
Yeah.
Yes. Yeah. I designed a descent probe for Venus once, and that was quite the challenge. But that's a whole other story. So Venus, it's about like being 460 feet underwater at the surface of Venus. The atmosphere is so dense. However, there is a plan that was mentioned at JPL that we now have the technology that we could terraform Venus. And we could send a series of ion rockets to Venus. These ion rockets would blow the atmosphere off and bring Venus to an orbit near the Earth. Venus is approximately the same mass and the same diameter as Earth. So it should be eminently habitable if it was not for this atmosphere. But it would take about 100 years of ion rockets going there to do this. So this is possible, and it would be reasonable for people to go back and forth, maybe. But that's this. No, the moon and Mars are both quite small. They have a very low surface density. This means if you made a little jump, you might go 12 feet into the air, type of thing. You all remember the astronauts when they were bouncing around on the surface of the moon in the so what does this mean? It means if we were to send people there, and this is why I think it's laughable that both NASA and our politicians and even the entrepreneurs say, let's colonize Mars. If we send people there, they're not going to come back. They're going to lose their muscle mass and bone density very rapidly. And to add to that, there's not a protective magnetic field, and they're going to be subject to showers of cosmic rays that will sterilize them and cook them in various unfortunate ways.
Wow.
So,
wow.
Go hold off that trip then.
Yeah.
Yeah, I would not book that trip.
Not voluntary.
I mean, yeah, that's about like going to see the Titanic in a composite submersible.
I know they were worried about the cosmic rays, even just sending the moon missions, weren't they? Yeah.
Well, yeah, I mean, and there actually is caution, about where we are in the cosmic ray, in the solar cycle, et cetera.
And you can't
sunlight.
terraform a magnetic field, can you? At least.
Well, it would be tricky to do. So
Or better gravity.
So the answer is I don't think it's a good idea, and I regard it to be political barnstorming to propose to do this.
Mhm.
It just doesn't.
Makes
I mean,
sense.
it may appeal to certain people that have dreams about Mars, but you have to step back and realize, is this a place where we could or would want to be?
Well,
It's not going to be fun for all.
Michael Enoch in the chat room is saying the FAA has to issue a license for a space launch in the US. But I guess my question is really, what is this drive for so many private companies to try to put people in space? What are they actually doing? And I just heard through the grapevine from one very concentrated effort. Oh, we want to take us and our families to the next planet over.
Oh,
I'm like, well, thank you. Yeah. Thanks for abandoning the rest of us.
let's
Would you
go.
put some of that expertise to healing this planet,
Yeah.
this little
Well,
spaceship?
can I answer the other question briefly?
Yeah.
And Michael started addressing that. Yes, there are controls about going to space in the U.S., but they're not really that successful. We're looking at several companies, each planning to launch thousands, literally thousands of satellites in the U.S. The same is happening in Europe, and similar things are being looked at by China and other countries.
That means a
So
lot of objects in space orbiting our planet. Yeah.
There's no international agreement really that's covering this well, nor, as far as I can tell, is there any serious discussion. Michael may be able to tell me differently. And we're having issues that sometimes very poor things are being put in space. For example, China launched a satellite, and I think it blew up. Maybe it was the booster that blew up, whatever. But there are thousands and thousands of objects that are just space debris.
Like shrapnel.
Like shrapnel, any of which could kill a mission or kill an astronaut. And so there are certain zones now which used to be very favorable to fly satellites, where people are doing scientific experiments. And Michael and I were both involved in one recently. You want to go much higher, which means added expense, but you can't do it. You can't really do it below. So the part of the thing is that there's really no adequate control over this. And there's a story which probably is true, that in a decade, a child will look up in the sky and say, "Mommy, mommy, what is that satellite that's not moving?"
A planet.
Meaning a star.
Yeah.
No, a
star.
star.
Star. Yeah.
Yeah.
I want to say,
Yeah.
if there's so much satellites to beam back on Earth to analyze Earth and spy on Earth and communicate just here, where's going to be the opening where, when you spend 5 years and $1 billion creating the next telescope, how is it going to have safe passage through all that stuff in the distant future to get out there? I mean, where's it's just
It's an issue, and some of the science is going to an area called L2, which is about 5 times the distance of the moon, and that is not yet corrupted. But
Careful timing, Michael says.
Careful
timing. Exactly. Let's go to some comments and go around the community a little bit.
You obviously know what you're talking about.
This to me is an opportunity for the layman, for the rest of us, to have access to astronomy in a fresh and powerful
leading edge way.
Exactly.
Yeah.
So don't be embarrassed
Don't be shy.
by your questions. Go ahead and ask them, and let's see where we go with this.
I'm never embarrassed by my questions.
I know.
Yeah.
Rex, hi.
So I just wanted to acknowledge Tony's humility and in what he's been speaking about, because so often, people get carried away with it. And my question, as a sort of a mariner, I was very, very aware of, astronomy was very much part of what you needed to understand sailing the oceans. But I'm also intrigued that as much as we're looking at further and further into space, we're doing the opposite as well, which is going into the microscopic, and it almost seems to be the same challenges. And you've said at one stage, that if we care enough, then maybe things will be revealed to us. And I see it in both directions, because I just wonder if human society, particularly Western society today, could be trusted to actually understand at these much greater and much smaller dimensions.
Well, this is a great comment. I'm fascinated by some of the numbers that are being used now. I'll mention the unit of time, an attosecond, which is 10 to the minus 18 seconds. It's about the time it takes for a photon to transit a hydrogen atom. And yet we're talking about measuring a few of these. So it's, yes, I totally agree. The microscopic and the macroscopic domains are offering amazing things, looking at very, very rapid. What does time mean when you're talking about an attosecond? I mean, uh, and and who says time flows forward even? You know, it gets to be very interesting.
What does time mean when you're talking about 14 billion years?
Sorry,
How
one
do
of the
we comprehend that?
one of the comments that particularly fascinated me was that said, in space, you think you're in darkness, but you're not at all. And the luminosity of the smallest objects that they've detected are so minute that we couldn't register them. So the world is certainly going to be different when we finally do begin to relate to these properly.
Thank you, Rex.
Absolutely.
Appreciate that.
Rex, thank you for the comments.
Yeah, those are good comments. Yeah. Thank you, Rex.
Put it in perspective. I appreciate that.
And Brian has his hand up, and I'd like to have Michael make a comment as well. Hello there, Brian Tucker.
Hey, hello, everyone. Hello, Tony. It's
Hi,
great to have
Brian.
a chance to talk to you, Tony. Always look forward to it. You know, in the world of disruptions that you're describing, and there are things that I'm kind of having to get used to as well. You know, for example, is the universe really 13.7 billion years, or do we have to let that go? Is that gradually going to be disrupted? But as I'm thinking about the disruptions, what are your favorite disruptions? What are your favorite ones that are really, wow, this is so interesting that we might not be tending to?
Yeah.
Oh, that we might not be tending to. Well, I think the question of exoplanets are extremely, extremely interesting to me. And there may just be more where I am. At one point, I was deeply into this and had NASA responsibilities for that. So that we're finding so much about planets and planetary systems that do not resemble our own. And as Laura says, perhaps Earths are rare. And there is a book out called Rare Earths. I mean, what are we going to find? You know, Habitable Worlds Observatory is assuming that we're going to get at least a couple of handfuls of habitable planets that we can observe. But what happens if we get none? Well, that's not a pretty picture. But on the other hand, it's going to tell us that maybe there's something far more unique about what's happening here on Earth
Or
than what
could
we
the
thought.
life be unique on these exoplanets? Wouldn't those planets then create life that would be adapted to those conditions? Or is the possibility for life such another narrow bandwidth that it can only exist
Well,
with certain parameters, but not this over here, not this over here, but just in the middle, the Goldilocks recipe? Yeah.
well, there can be many things, and we're finding things like life forms that are deep
Extremophiles. Yeah.
in extremophiles, deep in caves, way down deep in the ocean in thermal vents. We're finding life forms that are thriving in radiation. So the answer is yes, maybe, who knows? It's But what we're looking at first of all are life forms that may be kind of like us. Maybe that's very egocentric, though I
More
think
easily
we'd be happy.
recognized. Let's put it that way
Yeah,
too. Yeah.
yeah. It would be, yeah. I mean, I don't know what kind of life form we would have on the exoplanet that's rotating, that's orbiting once every 15 hours around its sun. You know,
Made of
everything
lava.
is lava.
Yeah.
Yeah,
And then
yeah.
why do we have
It's hard to
water bears? Why did nature create the little water bears, the tardigrades, that can dehydrate themselves and then go into cryogenesis? Why would nature do that? Isn't that interesting? What does that imply?
Well, there's so many interesting things in the world of biology and discovery right now. And I'm
Yeah.
not really qualified to go into it in great depth, but
Just posing the question. Yeah.
I will say that when I started doing exoplanets, there was a exobiology meeting at the Astronomical Society, and I think 12 people attended. Within a year, 250 people were attending, and now it's a huge field. So
Wow.
it's blooming, and I cannot claim I'm up to date on it, but there's a great deal of interest in all these things that you're describing, Laura, and what life could be. And but I think just watching and seeing what we find out when we have our next level of instruments, and with Webb even, we're seeing that there are some exoplanets that have signatures that could be suggestive of the presence of life, and that's exciting. Although via observational selection, there are several methods that planets have been discovered, and they tend to favor larger planets as opposed to smaller planets. So we may not be seeing a lot of the Earths. We're seeing probably a lot of the Jupiters, and they're in strange places, places we had not anticipated in their solar systems.
Mhm.
But maybe the Earths are there too, and we just don't know.
Brian, I want to give a shout out to the Deep Time Network. And what is the major quest there? To look at astronomical time, to look at the cosmos in a cultural, significant way.
Yeah, this is really a fascinating thing. Jennifer Morgan and others work on what's called the Deep Time Network, and we have a leadership program based on discoveries of science as it's applied to humanity. So I think it's really reconceiving oneself in relation to a time evolving universe, which traditionally hasn't really been taught and examined. So how does our life change as we consider that the very nature of the universe, it has all the elements for life to have arisen, and we're so fortunate for all of these early discoveries. It shows us what a miraculous moment we're living in. How do we apply that deep time knowledge to better the world? That's kind of the focus of the Deep Time Network with Jennifer Morgan.
Our universe and our place in it.
Yeah, thank you.
Always been a key.
One last question, Tony, is the observational field of the James Webb Telescope. I've heard analogies, and I wondered if you could clarify. When we're from Earth, is it as if we're holding a grain of sand looking out at the night sky? Is that the field? Does that describe the field that's being examined? Or is it something much more involved?
It's a larger field than that, but it's a relatively small field of view compared to some other telescopes that will have very large fields of view. I mentioned the Vera Rubin telescope. I think that has like several moon diameters of field of view on it. I don't remember the exact number. There are other telescopes that have much wider fields, but I think a grain of sand might be a little bit smaller than it really is, but it's probably far less than a moon diameter. Maybe
Moon
Michael remembers. I do not remember.
Thank
Yeah.
you, Brian.
Yeah, thank you, Tony, very much.
Thank you, Brian. Nice questions.
Let's bring on your colleague, Michael. If you would please turn on your mic and your video real quickly and join in on the conversation. And then also following questions in the chat room as well as we go along. Laura, can you see that? Because it's on your side of the screen.
Shoshana is saying, why did nature create tardigrades? That was my question. We could also say, how did tardigrades evolve? And can we ever understand why? I just think nature's purposeful. So there had to be a purpose to this, and how biology is so tied to our cosmology and to our cosmos and to our planetary parameters. That's what's fascinating to me. And that's another question of, we're designed to be here on Earth. All of life is designed by Earth, for Earth, to inhabit this planet and its particular parameters. You pick us up and you take us to another planet. How do you then integrate into that planet's parameters? As Tony said, it's gravitational pull, and it's that, it's da, da, da. I mean, and our receptor sites are so tuned to this frequency, this magnetic field. It would just talk about disruption. I just can't even imagine. So I vote make this planet more habitable and better. Let's take care of this one. But that's just me being political.
Well,
So
no, that's good.
yeah.
Michael said he has no microphone or camera on that particular computer. So go ahead and make
Oh,
comments in the chat.
thank
room,
you, and we'll
Michael.
read
We
those,
appreciate
Michael.
if you
Yeah.
follow along the conversation. I know Fred Smith had to just log off, but I wanted to mention Fred Smith and Tony were roommates back in college.
Oh yeah, we've heard
So
those stories.
It's so
Yeah.
interesting that we can have, have the view from the Vedic astrology, Vedic, perspectives, along with the astronomy, that the two of you would seem so vastly different and yet so closely together in the way that you perceive.
Because
the
our
world.
ancient cultures, I mean, we have our screens, right? We're so we're so addicted to our screens. Look at their screen, the night sky,
Yeah.
right? And
So
we
I'm
can't
sure
we can't see our night sky as well as they did, can we?
Right.
We can't. It's light obscured for the
So I'm
most
sure
part.
you and Fred have some fascinating conversations.
So Tony, I want to talk about our drive to explore. I mean, isn't this one of our key best attributes for humanity? Is like we want to know what's around the next corner,
Mhm.
right? What's on the far horizon? We have this drive to explore. And so to me, to go take it to space, and I'm talking about the inner space, right? As well as our outer space. It's really such an eternal quest. And is that part of what drives you as well? What is the unknown, and can we peer into it? Can we go around the next bend ever further and further and further? Isn't that just part of what drives us all?
Well, I think we're all designed to do
Even the
different
hobbits.
things.
Yeah.
I think we're all designed to do different things, and my life seems to be consist of a progression of events that are preparing me for the next event. It's not that I planned my career in the path I've taken. I mean, I've been attracted to astronomy. Uh, I ended up in a very different path than I envisioned in graduate school. I envisioned being more of an academic, but it turned out that I have a lot to offer. I've had more to offer, I think, in terms of developing instrumentation. And for a while, I worried that was not astronomy. And then I was talking to a colleague, one was really pretty much the starter of the exoplanet field, John Trauger. And he said, "No, Tony, developing the instrumentation that you're doing, this is exactly what astronomy is. It's opening the windows to
Opening
see
the
what's there."
windows, opening the
So
bandwidth.
I accept that. I was going to become what my dissertation was on, an expert on stars that go around each other, sometimes several times a day, and are actually fairly prevalent in the sky. It's not known that over half the stars are binary, but that's another story.
What?
But
What? Over
I was
half the stars have a twin. And how does the star, and like our day is short comparatively. How do they go around twice a day? How does something move that fast? They're huge. That's a lot
well,
of
they're
distance to cover. How's that even
and
possible?
it is, and they become gravitationally distorted. They're very interesting objects. They're no longer spherical, and yes,
Oh my
we can say
gosh.
a great deal about them. I was measuring them in polarization. That was my specialty, and but it seemed that almost immediately I the switch was flipped, and I went into industry, and pretty soon I was developing a mission going to Jupiter, and then it went on to develop other things.
So your parents were right to encourage you towards that engineering background, because without it, you wouldn't be able to do in industry what you're doing today.
Well,
Is that true?
it helped, and it helped. It gave me a background that I can deal with things that, well, many astronomers are very adept at instrument development, but it's nice to have that in my quiver that I've studied I've studied mechanics and electronics and continuum and devices and a lot of things in depth. And I always managed to, I had, by the time I graduated with a mechanical engineering degree, I had far more astronomy classes under my belt than most astronomy majors.
Oh my
I just,
goodness.
I just, I just skipped baby astronomy and took
It took the
this other
advance, right?
class instead.
Drop in the
Yeah.
deep end of the sea. Okay, here's a question I've long had. Are the laws of physics, how can we assume that the laws of physics that operate in our little neighborhood of the cosmos are the same in some of these other extreme sectors where these violent explosions happen, or this, that, and the other? How can we assume that the laws as they operate today aren't localized?
Well,
Why would we assume they're
well,
universal? Some of them I'm
well,
sure
here's-
are, but
yeah.
how does gravity operate here? Why isn't it different over in this other neighborhood that's very different from ours?
Actually, it's a very nice question,
Thank you.
Laura, and I will say this, that what we can do is observe. And if we see that things are not behaving the way that we can predict it with our models, immediately we become interested that maybe something else is operating. This is how dark energy and dark matter were discovered. We had to introduce something else because the universe was just acting like it had much more mass than it did. And yet we were not seeing it with all the tools we have, which should be successful in knowing it's there, going from long wave radio to the shortest wave gamma. We're not seeing it, but we know it's there because of the way matter is behaving of that. So the answer is, yeah, the universe is an amazing laboratory where we can see things that are really different. And one of the things that I noted when I went up to visit Los Alamos with
Yeah.
uh, with John Mather, by the way, the Nobelist, um, and that was that many of the people that we were meeting there were trained as astronomers and were doing astronomy. Now, why is Los
Ah.
Alamos hiring all these astronomers? It's because they know about these very high energy, amazing things.
There you go.
And how are they applying them and making use of them? Okay, the other question I have is, I heard uh, uh, Stephen Hawking once say, why couldn't it be a bang bang universe? Why couldn't it be an oscillating universe where the big bangs send stuff out and now it does its thing? And now the black
Yeah.
holes are slowly in different areas, sucking it all back in. And maybe it's
Mhm.
all collecting and then will explode again. Now that's an oscillating universe. That's bang, 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 bang. How do we know that it's one bang as opposed to multiples and different
So,
sequences of
and
bangs?
I'm going to say, in an absolute sense, we don't know, except where we watch the accelerations and for accelerations and decelerations as we find various ways to measure velocity and distance, etc. And this may sort out differently, but right
Because
now,
yeah.
yeah,
Because my theory, my question really has to do with chaos theory. And as it was explained to me by one chaos theoretician, is that there are many more patterns in the universe than we know, because we only see this timeline. But if you pull back, perhaps some of the timelines, some of the periodicities are way beyond us. So what we think is a one event could be a series. We're just seeing this much, not this much. So there are patterns that we don't even recognize because we're seeing in too short of timelines. So that would apply to the bang, 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 bang. We're just seeing this one. We're not seeing the bang, 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 bang. We're just seeing this much. So how could we even tell? We're not alive long enough to
well,
make
what
the
we
observations.
yeah, what we can do, we're not, but we do have historic observations. We have observations over time. Of course, every generation, every decade, we're making measurements much
Wider and
better. So
wider.
sometimes it's very hard to compare a measurement that was made in 1950 to a measurement that's made today, because the technology and the precision is vastly higher now.
But I'm
So
talking about, you got 14 billion years here. What if you've got 100 billion years? How many oscillations
well,
would
well,
you see?
well. I mean, who knows? I mean, we even have the question of
Exactly.
parallel universes. There
Right.
are a lot
Yeah.
of interesting things that could be, and what we do is look at the data and see what the consistency is, but it's not dogmatic. I mean, if there was evidence emerging that made it look like an oscillating universe, nobody would be slammed because of that. It would not be disappoint anybody. It would be, wow, okay, we have this new data, and now we can look at the universe in a different way and apply different models. It would be exciting. It would not be
Well, indeed,
There
but
would
you
be no,
earlier
there'd be no,
referenced the Big Bang won out over the Bang Bang. And so I'm thinking, well, how can we even make that
well, let me correct my
termination as
language.
yet? Yeah.
That winning out means that it's the prevailing
Favored, but not
preferred
cemented in
prevailing
stone.
preferred
Yeah.
theory. No, nothing is cemented in stone. I mean, except that the scientific method itself involves testing what you're doing with data, etc. And
Let's
you continuously look for a consistency that can be verified and repeatable in some sense by not only myself but others. That's part of what we do.
we
And
I guess we need to
I-
understand that we're really sitting on shifting sands and that our worldview is continually evolving along with us.
absolutely.
Yeah.
And just like we're kind of laughing at the great nebula in Andromeda that was being talked about less than 100 years ago.
Yeah.
100 years from now, I just can imagine the laughter that the new directors of Kayamunga Institute will have about what people believed back in
The Dark
2023.
Ages.
Yeah.
Yeah. Oh,
So I think you better write a letter to the directors of CI
in the
in
future.
in uh, in 2123 to be open in 2123.
Right. Well, in our
Oh,
time capsule. Yeah, we'll put
yeah.
that. You've talked to me about the life cycle of the stars, and I think that is so beautiful to understand. We're all evolving, even our cosmos, even the stars, even everything around us is on a journey and it's changing and evolving. You started out by saying the one constant we have is change. Could you tell us about the life cycles of the stars and what we know, and how most of
Oh,
them, what, are in middle age now? And how is it all working? What happens when they've all lived
well,
their life and they've all burned out and all we have is a bunch of ash? Then what?
well, we have short-lived stars and long-lived stars, and
Yeah.
actually, I think you've quoted Joni Mitchell. Yes, we are stardust. That's what
Oh,
we
yes.
are. There are many generations of stars that have gone on, and this is what has created the heavy elements. I mean, we started out pretty
We are
much
made of that. Yeah.
with hydrogen and helium, and then we went through a series of things, and getting heavier than iron involved stars exploding. I see that Kelly has a question here.
Yes, Kelly.
Well, we are what? We are born of the furnace of the stars' death throes, aren't we? They're
Absolutely.
smashing elements
Yeah.
together, and then those coalesce into planets, and then that planet, through some miracle,
Yeah.
has a biosphere, and then life of. I mean, it's just a miracle. Hello, Kelly.
Hi. So I just kind of wanted to say this has been amazing, Tony. I'm always excited to hear everything that you have to teach us, but this clock thing is really intriguing to me. And you were asking about what do we think about a clock that runs backwards, but you really never gave like a full answer on what you think about it.
Thank
I was
you.
looking at your directions in the circle, and I was going around like a clock, like navigation, worldview, astrology, sacred art, architecture, all the way around. And then I just went the other way and I said the directions, seasons, hunting, planning, extreme. Like seems like it could start on both sides. And I just
Well,
thought that was kind of telling. And I was wondering if you'd like thought about that in the clock sense when you made this graph.
well, I knew I wanted to make it sort of elliptical, actually circular. That was sort of the vision I had when I woke up this morning. So it's but yeah, it's well, thank you. Here, so I just wanted, I did not want to elevate anyone above the others. Well, I kind of wanted the dogma to be down lower, I guess,
Right.
but the
Oh,
others, yeah, are so are all quite interesting to me. So
I really
um,
love that you put certain things today because I am just learning, and learning from you as a friend has been like you help me understand a lot of things that I wouldn't normally understand by reading a book. So, you're talking about like calibrating the horns and the beach ball and, the four moons going around the earth, like things like this, like are so
yeah.
visual. And I just want to say thank you for explaining things and such a way that, people that have been doing this for years can be here, but people like me can also still be here, and you have like a foot in both worlds. That was when you were talking. That's the only other comment I wanted to make, was when you were talking about how you dreamed about the moon and the stars and, the blue sky and all of it. Like the Naskapi, like Algonquin people would say that you're obligated to interpret your dreams. Like you're obligated to express them, whether that be in art, whether that be to figure something out. And me and Laura were discussing this recently about art and about your dreams. I mean, you were just saying, why did this happen? And I don't know how this happened. And I just really wanted to say how special I think you are, that you really dreamed these things and you listened to your dreams, and you went through with this obligation to figure things out that some people wouldn't have tried to figure out since you were a young boy. I just think that's beautiful.
Thank you for that. You also got a compliment in the chat room that when Tony explains things, I can understand them. So that's a very nice compliment to receive. Thank you.
Good
Thank
one,
you, Kelly,
Shelley.
so
Thank
much
you.
for your appreciation of this.
Yeah.
Yeah. I also want to add to your list, Tony. I want to add that there's cultural cosmology and the star lore that so many cultures have held with anchoring to the stars and the planets and their movement through the year. So much mythologies and stories and folklore and archetypes have been hung on the celestial bodies. And the metaphorical language, the mythopoetic language, the language that we have when we hold the stars and the heavens close to us, it's such a realm for us to anchor our own desires and dreams and projections of self and our hopes. And the heavens have meant so much to humankind. So it's been such an important, and I think our first screen of our minds and our imagination. So I would add that to your chart. And also to say, I don't know how much time you can spend with us. We're at the close at the top of our hour, our second hour with you, but it's just been a delight to really add the perspective of an astronomer who we don't get to rub shoulders with all the time.
Actually, if I could
add, and also a scientist mystic who you are, and that one who's also done our work and seen the stars and seen the cosmos through the inner eyes, the inner senses, as we do in our work. So it's just been such fun to have you as a friend and advisor to this institute, Tony. Thank you. I know one of your more important roles in life.
Actually, and if I could add, this became like a primer. This is the astronomy perspective we need to have a foundation for. It's okay that we didn't have the full slideshow today. I'd much rather have this discussion. Now you've gone through this program with us. Let's do the next program with Tony, where we can go deeper into the next level. So I
want to see what I loved what the Hubble telescope gave us. I want to see what the James Webb is delivering to our eyes with you as a guide. I want to see what it's showing us in the infrared.
And that's a different talk almost. So that's really fabulous.
Different talk.
I think it's great.
So it worked out that it was in two parts.
We'll take it. Yeah.
So
well, thank you, Tony. And the other thing is, maybe not everybody knows, is that we had scheduled a different guest and the guest got ill, couldn't perform, and you immediately said, I'll do it. And here's, off the top of your head, you put together this amazing presentation today, as usual. This is the kind of conversations we have with Tony on a weekly basis. We call him on the phone and it's hard to get off the phone.
Tell me about the life cycles of the stars, Tony.
Yeah. But by the way, Tony, would you please share with us? Yeah, exactly.
We know all of this. Oh my gosh.
Exactly.
And it's just so much of our philosophy is anchored on the heavens. I also just want to give credit to one little insect who also charts the stars. The dung beetle.
Okay.
The dung beetle. So celebrated, right, in Egyptian iconography. But the dung beetle pushes this little ball of dung, which is his little fertile planet for himself, aligned to the arm of the Milky Way overhead.
Right.
That somehow this little dung beetle has sensors to imbibe starlight and to know, oh, I'm going to follow the line of the Milky Way. And also, I want to tell you how beautiful it was when Paul put together his labyrinth. I wish I had a picture of this labyrinth. he put together, Tony, because of you telling Paul, hey, when you give us your talk, one of your first talks for us on Conversation for Exploration, hey, everybody can build a megalithic marker in their own backyard. So, hey, choose a point, Paul, in the backyard. The best point is where you can see sunrise and sunset. So Paul picked the one spot where he can have direct line of sight to both sunrise and sunset. That was out the door. We started to stand there, Tony, and we started to mark with the gnome on, all the equinox and the two curves of the solstices where we could when we were here and da-da-da. And then Paul got the idea, oh, why don't I put up my own Stonehenge? He calls it Domehenge, my own. So then he contracts to get a guy who's got the equipment,
because we
got the contacts at the quarries.
9
Hey,
foot
I
tall
need some
stones.
big stones. I want some big ones, not little ones. I want big stones.
Right.
Yes, size matters, my dear. Yes, indeed.
Yeah.
And let me get 10 of them. So the guy comes in with his axles and he's digging Paul's, 30-foot circle because we had to level the ground. He got some guys with shovels out here and earth movers, level the ground. Almost broke his axle, this guy putting in these giant, beautiful stones. And then Paul gets his gnome on, and then he does all this. But then we had a pathway. We had a pathway where, we have to go to the front door or the back door, the side door, and then we have to go down below. This is where UPS delivers. They come up some steps. They have to make a direct beeline and deliver a package, right? So this was, so Paul goes, how do I do a labyrinth here? And I go, well, Paul, you really have to have something level where it's not going to trip anybody, because that's where everybody comes to our door, right? They come right through that space. So you have to do double duty. Well, I want a labyrinth. I go, well, Paul, you could do a labyrinth over there or there or there.
Yeah.
No. Has to be a labyrinth here. So I'm like, okay, darling, you design your own labyrinth and then make that pathway. Well, it has to be no stones. It can't be tripping. It has to be a straight path. I go, Paul, here we are as we walk the labyrinth. We're going to make this leap across the abyss. We have this metaphorical abyss where there will be nothing, right? It'll be a step or two, but we'll know. Then the path picks up on the other side. So this we can create our own metaphorical language here for this labyrinth. And by the way, this labyrinth, this pathway, from pathway, open pathway to pathway, is in alignment with the Milky Way. So I'm like, oh, Paul, this is so perfect. This straight path is aligned to what the Milky Way's arm is overhead. So as above, so below. You've got this pathway, that's so storied. The land, the realm of the ancestors, the pathway where Isis and Osiris float their bark, da-da-da-da-da. So it's so perfect, Paul. The stars have aligned in the perfect place where we can have so many layers of meaning. So show your labyrinth. Oh, here it is.
Yeah.
This is the arm of the Milky Way. This is where UPS delivers. And also,
it doesn't have anything to do with
yes,
UPS.
it is, because it's so practical,
Oh
right?
my gosh.
Well, it is.
Okay.
It is. It had to be kept clear.
Right.
But during our recent event, when we had 14 people, we couldn't fit in this teeny tiny circle. So we all lined up in a straight line to view the sunrise and then
directions.
to view the sunset on occasion. So it worked out all perfectly. So thank you, Tony, for inspiring us to create our own megalithic marker in our own backyard.
Yeah.
Worked out nicely.
Yeah.
I'm still waiting for the time capsule, Paul.
No, that's a ceremony you have to do with us.
Yeah, well, and now
Yeah.
we got plenty of data to add to the time capsule as we go along. And now we have community gatherings, which will add to the time capsule. But anyway, sticking with you, Tony, and not about us today, I really wanted to honor you as
Let's see if you have a picture.
taking astronomy to the level of the individual, being able to make it accessible and something that is inspirational. Because for me, the journey that we're on, and I started out today's presentation talking about the field of observation, and that, Dr. Goodman was previewing and seeing these things in the prehistory world that had representations, and she wanted to decipher. And like that, she had an internal message, something more to this that has meaning. And like that, that's the way you view astronomy, is you're taking a foot in both worlds, where you can look at the stars, you can be a scientist, you can be an engineer, you can be a mathematician, but it's that internal dialogue as well that really drives you, that you're a poet and that you're an artist and that you have this other part of your personality that you're sharing. So,
And here's
Yeah.
a picture of our group shot.
oh,
Around, and show,
That's okay.
show the equinox
yeah,
that you truck. Show the
I-
picture.
no, I don't have
Very,
time.
very
To,
cool.
that's okay. I want to
He
stick with
trucked
Tony.
the equinox.
Yeah, we have a beautiful visionary. We'll do that for another presentation. But I wanted to stick with Tony today. And so, Tony, again, as I just finished
Well, I just
saying,
wanted him
I-
to know that you're following all of his prescriptions.
his inspirations. Yeah, good,
I'm coughing. I
Well,
can't say goodbye.
good. Let me do the speaking for a moment. If I
Right,
can have the
excuse me.
microphone
Thank you,
for just
Tony.
one moment, Laura. Wonderful. Well, Tony, and the other thing in closing is that, friendship. Friendship is something that it's rare in these days and age to have somebody that's there, always there for you, that you share so much of your heart and who you are as a person, that you don't take your status as a scientist and ever wear that on your shoulder as if it's important. When we have dinner to conversations with you, you're always asking everybody else about what they're doing. You never talk about yourself unless if we force you to talk about yourself, because you're very generous of the heart and you're an individual that delights in other people's success and their research and their understanding of the universe. You continue to do that same sort of investigation with people that you do with the stars. And that, for me, is what makes you such a special individual. So I guess what I'm saying is I love you, man.
And I you all too. It's
Yeah,
it's just wonderful knowing you. This accident of meeting you, amazing.
yeah,
And everybody who's on. I mean, you all seem like friends. You're fellow metaphysical mountain climbers.
yeah.
Oh, I like that.
I like that too.
I like
Yeah,
that.
yeah,
I know.
yeah.
Thank you so much, Tony, for
Yeah.
yeah.
Thank
Let's-
you all for listening.
Thank you, Tony. I'm
All
going
right.
to have everybody unmute their mics and they can all say, this was a fantastic introduction and integration to Tony's research and his worldview of astronomy and humanity together.
Part one.
Part one.
Images next. Yeah. Thank you, Tony.